Here we go. Thank you, Cece. I have a special announcement to make, which is that there is a sign-in sheet. We will provide a link to a Google Drive where attendees can sign in, and we would be very grateful if you would take the time to jump over there. And now for the introduction. Dr. Thomas Wiecki is an advocate and leader in the space of artificial intelligence and especially in Bayesian modeling. I first discovered Dr. Wiecki through social media, actually several years ago at this point, where he was posting artificial intelligence examples and work that was not like anything else I was reading or experiencing at the time. So I'm really pleased that he has accepted our invitation for today. I have since watched a lot of YouTube videos. I signed up for an intuitive Bayes course and listened to multiple really interesting podcasts on this broad area of Bayesian modeling. And what I've discovered is that Thomas is among a small group of true leaders in this space that a lot of them, like him, were trained as scientists, but then branched out to really explore what's possible with some of the contemporary technologies, especially this probabilistic programming business. These people have gone on to do influential work on Wall Street or real Moneyball examples like working for the Philadelphia Phillies. These days, Thomas is the co-author of an open source library for doing probabilistic programming, PyMC, and he is the CEO and founder of PyMC Labs, the Bayesian consultancy. His initial PhD work was at Brown University, where he studied computational cognitive neuroscience. Thank you, Thomas, for being here, and we're very excited to hear your presentation. Please go ahead.
What an amazing introduction. Thank you so much for having me. Thank you all for tuning in and being interested in Bayesian modeling and what that can contribute to today's debate. So I'm particularly excited to speak to you all today because this is something that really is the combination of, well, something that I have been working on for a very long time, Bayesian statistics and PyMC, and combining that with causal inference. But then the last piece will be something I've never talked about before, which is how to then combine that with large language models, which of course all the rage these days, to perform what is usually called synthetic experiments. And for me, this has been something that I've been thinking about a lot. One of the reasons is like we statisticians don't want to be left in the dust with the LLM revolution. Is there still going to be a place for us? So this is my attempt to stay relevant. But I also think it makes a lot of sense. So I want to start us off just very broadly, talking about why do we even do data science? What is the purpose of data science? And that might seem, actually, it's something that I thought a lot about. And I think I have found an answer that I currently like. See if you agree. But before that, what are some of the other answers that, well, actually, I used to think was the purpose of data science? So this breakfast cereal morning comic has the interviewer, the journalist, talk to the scientist. Why is it important that we abstract any matter? The scientist is like, that's freaking awesome. So this is, I think, used to be like just good enough for me. Like when I started my PhD research, I thought it was all just like super exciting, using the latest and greatest technology, fancy mathematics to solve really difficult problems. And I still think that's amazing. So I still love that. But maybe not the only reason why we should be using these tools, right? Maybe it's to predict outcomes, right? So we want to be able to make forecasts, predict the future, right? Vic already mentioned the example with the stock market, right? We want to forecast things. So that, I guess, that sounds more relevant, right, to business questions, being able to forecast next quarter's earnings or something. But but even that, like, learn about the problem, right? Maybe there's something more that we really need rather than just like the forecast. If we just understand what is going to happen, but we don't understand why something is going to happen, is that really so relevant? Well, that leads me to the next proposal, which is maybe, and this is what I guess have been thinking the purpose was over the last couple of years, is to generate insight, right? We don't just want to be able to like shove data into a black box predictor that makes amazing forecasts. We also want to be able to really learn something about the problem that we're working on and generate insight from this, right? And Bayesian modeling is perfect for that because it is not black box. It is a model that you can understand, that is built on your own intuitions and knowledge about the problem, right? You can investigate it. We're going to talk about that. But even that, actually, I think is a little bit too short-sighted, where it's better to understand why something is happening, but you really need to understand how something is happening and be able to influence it, right? So ultimately, I think what the purpose is to make better decisions, right? So only learning something and understanding why, if we can't do anything about it, right, is not all that valuable, right? We want to be able to influence the future and make better decisions. So for that, we need all of the above, but this is ultimately what it. So let's start with a simplified but nuanced and real-world problem, which is, imagine you're a data scientist at a standard e-commerce company, maybe HelloFresh, and the marketing team wants a very simple question. How effective is Google Ads in driving sales, right? They want to know how much they should spend on Google Ads to meet their sales targets. And we're going to make one simplifying assumptions here, which is not that realistic, but it makes the whole setup, it makes the example more illustrative and work better. We can relax that, it's no problem. It's just for didactic purposes. And that is that the marketing team turns Google Ads on and off, right? So on one day, either they turn it on another day they turn it off. So it's a binary variable. And here is the data, right? So they send us this, and we have the sales on the x-axis, which is just z-scored, right? So it's centered around 0, and we can just do a histogram, and we have sales on days where we didn't do any Google Ads and sales for days where we did do that, right? And if you haven't looked at data a lot, then maybe you think like there's only small difference here. If you spend time in science, you're like, wow, this is like a huge effect, right? And that's true. So no matter what kind of statistics you do, right? You can do frequentist statistics, run a t-test, can do a Bayesian t-test. If you wanted, you could fit like a logistic regression model to like see how well you can tell them apart. They would all give you the same answer, which is that yes, there is like a significant difference between these two groups, and Google Ads leads to an increase in sales. So great. So that's the answer we were looking for. Here's another way you can do it. It's called a marketing mix model, which I might talk about later if there's time, which takes more complexities into account. But it doesn't really matter, right? The point is, no matter what we do, we get the same answer, which is like, yeah, clearly there's an effect here. So awesome. We take that back to the marketing team, and tell them, yeah, if you want to increase sales, then this is like a great way to do it. But there's just one caveat here, which is what they neglected to tell us is that they also run TV ads. And those TV ads are obviously also going to have an influence on sales. And even worse is that in order to maximize the impact of their TV sales, that's when they also turn on Google Ads, right? The idea is, well, we run these TV ads people are gonna go online and look for our things, so that's where we want to run the Google ads to drive sales even further. So they mean well, but they just screwed up our whole beautiful statistical analysis by introducing what is called a confounder. And that means that, like, well, if these before, right, we thought like, oh yeah, Google ads drive this effect, but it's possible that Google ads actually has no effect, right? But that this drives sales up, and then this influences Google ads, right? We already know that. And then it just looks like this, right? So the effect could be purely driven by the TV ads on sales. So how do we figure that out? So this is now where it becomes a little bit more difficult, but fortunately we have a powerful tool, which is the data generating process. And this is really, for me, I think the core benefit of Bayesian modeling the way it's often being done, which is that we think about, we really try and map the problem that we're working with to a corresponding model. And that is completely different than what you usually do with machine learning and deep learning, whatever, right? And this is what Vic alluded to earlier, which is like, this is a different approach, right? So this is much more like the thinking approach, right? Where like spend a long time thinking very carefully about your problem and thinking about how was my data generated, right? This is ultimately how you're thinking about this. And I mean, I already told you how the data was generated, right? We have this, right? And we're going to assume that this is basically what we have going on. And what we then do is, well, we just take what we know about the problem and how my data was generated, and we just map that one-to-one to a causal model, a structural causal model, a Bayesian model. That's all more or less the same thing, right? The core idea is this is not just a black box model. We just shove a bunch of data in and we get predictions, and we don't know how those predictions came about. This is, we take the data, we take our understanding, build a model, and then we fit that to the data. And we have three nodes here, right? So we have our TDS, C, we have our Google search, Z, and we have our sales, Y. And one thing that we always have to do, because we're in a Bayesian framework, is specifying prior distributions. So we can say that this is distributed according to a normal distribution. This is quite so important. And then here we have a inverse logistic, a logistic regression that estimates, okay, what is Z is an effect driven by an intercept term and C and a regression coefficient, and then Y is driven by an intercept term, a regression coefficient for Google Ads, and a regression coefficient for TV ads. So basically two linear regressions going on here. And this is a logistic regression because Z, as you remember, is a binary variable. So whenever we have binary variables, that's when we use logistic regression. And the corresponding likelihood function for binary events is a Bernoulli distribution, the infamous coin flip distribution, right? So that's just like some statistics terminology. If that didn't make a lot of sense, it doesn't really matter. Really, the core is we're mapping this to this structural causal model. So that'll work, and we're gonna continue with that, but I just wanna take a second to say that that is actually not enough. So far, what we've done is we have this logic of like saying, okay, well, we're gonna take this data generative process, the DAG, and that describes the business relationships. And that's really powerful, right? So this is the thing that we can use to communicate to stakeholders, right? We can, we can really gain insight into the problem and all these things. But nonetheless, ultimately, we're still going to fit this to data, right? That's the next step. And whenever we fit something to data, well, we have to make estimates, right? The data is going to be noisy. It's going to be maybe not in the quantity that we want, right? So there's always going to be noise in our estimates. And usually you just pretend that that's not the case, right? And that you hope that, but maximum likelihood estimate, like whatever machine learning algorithm you do or whatever neural network you train, you always just find like a single point, right? That like does give you the best predictions, right? But that doesn't really tell you anything about how stable that point is, right? Like maybe that best fitting parameters value is the only one, right? And every other value like just doesn't give you any good results. Or vice versa, no matter which value you pick, actually, they all give the same result, right? I mean, both of those would be interesting to know, right? Wouldn't you want to know that, like, well, actually, I don't even have to fit them all, right? Like all parameters give essentially the same results. I mean, that also tells you something about the problem that you're working with. So if we want to make better decisions, not only do we want to know how our problem looks like, we also want to know what is the risk of having estimated the wrong thing. And here I want to zoom out a little bit and think about all these different approaches in this 2D grid. And on the x-axis, I have uncertainty, right? How do we think about uncertainty? That's the point I was just making. And on the y-axis is interpretability. And interpretability essentially reaches from black box ML, right? So you just like train a random forest, right? And like, who knows what how these things correlate, right? It's just fitting this crazily shaped thing to maximize predictability through any means possible. And that's great, right? If you only care about predictiveness, then cool. Like these algorithms work super powerful. But if you do want interpretability, it's not going to cut it. So that's where maybe you want to run statistical correlations, right? You want to know, okay, what variables are correlated with my outcome, with each other. And if you really want to go to the next level and deal with things like confounders above, right? So that's where correlations break down, because we saw that my Google ads and sales were correlated, but correlation isn't usually what we're looking for. Really, to understand the problem and make better decisions, we need to understand causally what's going on. And so that's at the highest level of that ladder. And then on the uncertainty, we have point estimates. That's what I was saying earlier about when you just run a machine learning algorithm, a neural network, whatever, you get point estimates, right? Just a single number that tells you this is the best fitting parameter value that maximizes predictiveness. And then there's frequency statistics, and then there's Bayesian statistics. People argue too much about what the pros and cons are. You can do both. I like Bayesian statistics. It gives a lot of flexibility and interpretability. I think the most powerful way, actually, the most powerful thing about this is more on this axis. And then, yeah, you do want to, and it just happens to turn out that like you can build these causal models particularly well in Bayesian framework. So they go very well together. That actually I think is more powerful than like the nuanced discussion of like p-values and whatnot. So now that we have this nice grid, we can place things on it and say, okay, well, scikit-learn, which is an amazing library, which I love, does point estimates and offers a whole bunch of really powerful black box machine learning algorithms. Conformal prediction came out more recently, also black box machine algorithms, but now we're adding uncertainty to our outputs, more or less in a frequent. Stats models, really cool package, allows you to do statistical correlations in a frequentist framework. Do-Y is a cool package from Microsoft, which allows us to estimate input a causal DAG, and then from that, essentially, do causal discovery and a whole bunch of other things, and also fit a structural causal model as we see here, even though it's still pretty rudimentary in terms of like how it's representing point estimates. So it's basically this idea where I said like, yeah, we don't want to be fooled by randomness, right? So here, I mean, they're adding some frequentist tools, but the focus is much more on the causality. And PyMC now, I place here in the upper right corner, it's definitely Bayesian through and through. And the models that we tend to build are usually causal by nature. So let's look at what that looks like by combining the two. And I know showing code, if you haven't really seen PyMC, this will look probably like garbage, but maybe some of you will at least get the high level overview. If you don't follow this, it's not a big deal, but the main point that I want to make is that each of these nodes here corresponds to a single line of Python code. So we have parameters for C, we have parameters for Z, and we have a noise term. And then here we have our likelihood functions. For every parameter that I have a prior distribution, right? This is what I think about likely plausible parameter values before I've seen any data. And this actually allows you to inform your model even more, right? So there's two ways that Bayesian informs the model by expert knowledge. One is by just the structural graph, right? So what is my belief of how the data was generated? And then also, how strong do I think these associations are before I actually have fit any data? And here we're just being a little bit vague and saying, okay, well, on average, I think it's going to be close to 0. So that's why I place a normal distribution. And because there's not just a single C parameter, there's the intercept, there's C to Z, and there's C to Y, there's shape 3. And then we have this other one for the coefficients of Z, we have our sigma Y, and then here I'm not going to go into too much detail other than saying, okay, there's an observed argument for things that we observe, right? So we observe on which days we had run Google Ads. So this is going to be binary, and we observe the sales as well. And then this is just the linear regression. And here you can see basically I have an inverse logit and a Bernoulli. I have a Bernoulli and inverse logit. So really the hope is, well, what we try to do with PyMC is take this, the statistical model description and make it as close to Python code as you can. Okay, so the other cool thing about this is that when I have this model, that's actually all I have to do. So then the estimation process is sort of auto magic. I just have to hit what I call the inference button, and then it'll run a so-called sampling algorithm, Markov chain Monte Carlo, MCMC, and that will do all the work for me, right? So Bayesian statistics, as you maybe know, has been around since the 16th century, but it wasn't used because we just didn't have any tools to actually estimate it, right? And that's why frequentist statistic was invented, because at least we could really estimate it, right? Now, we don't have to do analytical solutions to this model. We can just do estimations, approximations using MCMC, and these algorithms by now are so powerful that they just like work on almost every model that you throw at it. Incredibly powerful and scale really well. So this problem now doesn't really exist anymore because we have great algorithms and powerful computers, so we can actually do proper Bayesian modeling. Don't have to refer to frequent statistics. So, and when we do that, so we run our sampler, and this is what it spits out. Well, this is what it spits out after I do histogram. So for every parameter, so I have the slope, right? How strong is the influence of C on Z? How strong is the influence of TV on Google Ads? Quite strong. So the true value, I generated data here, so I know the true value is 1, right? So whenever I run TV ads is also when I run the Google Ads. So that correlation is super strong. And my model now, this is the blue, histogram here recovered this. So note that this is a distribution, right? It's not a single value. That's the point I was making with the uncertainty estimation, the uncertainty quantification. We don't get point estimates, right? We don't just get a single value. It would be another line here. We get a whole distribution of values that tells me how plausible these different values are. So basically what this is saying is error bars. From 0.9 to 1.02 could be anything within that range. And obviously I get that for all my parameters. So this is the output of the sampler, is my so-called sphere. And that's cool, and that's business have been doing this for a long time. We can do a little bit better by combining this with the, again, borrowing tools from causal inference, which is the average treatment effect. And if you read the book of why, this is really the contribution here is this so-called do operator. And essentially what this does is, well, okay, so what do we want to know? We want to know not what is the influence of the z on y. What we want to know is if we artificially were to turn on and off Google Ads, right, irrespective of what the TV is doing, what is happening then, right? How big is the influence if I go in and I just decide I run an experiment, right? That's really what this is. I run an experiment where I say, okay, I'm gonna run on 100 days, I'm gonna run Google Ads on, and then 100 days I'm gonna run Google Ads off, and then I'm just gonna compute what is the difference in sales, right? That's what the average treatment effect is. And that's really the thing that I'm after. And that, critically, is a causal thing, right? This is not a correlational thing, because here I pretend I'm running an experiment, and that allows me to, make causal claims. And this is a new addition to PyMC, where we have the do operator. So just PM do, we call the model, we say Z, which is the Google Ads, we set to 1. And we create another model where we set it to 0. So these are my two conditions. And then I call sample posterior predictive. And I get an estimate. And again, because I'm in the Bayesian framework, I get a nice uncertainty bound here that tells me that my average treatment effect, the way I estimate it from the data, is very little. So it's very close to 0. And I mean, obviously, this is the way I designed this example, but it's quite striking, right? Before, the message to the marketing team was like, oh yeah, like Google Ads is amazing, you should run more. Now the answer is actually Google Ads has nothing to do with driving sales, right? We're pretty certain that it's 0 or very close to 0. And that was a meaningless statistical association, which didn't count for the confounding variable. So taking this Bayesian causal inference approach, we get a better estimate, and we get the correct answer, and we get uncertainty. So all of the good things. So as an interim summary, we really want to reason about actions and outcomes rather than just making predictions, right? What good is it if you can predict something, if you actually can change it, right? We want to be able to influence the future. And we do that by building a model that is not a black box model, but a model that is interpretable and maps the business processes as a causal DAG by mapping the data gen process, directed acyclic graph. And then once we have that, it's cool because we can go in and surgically change various things and run hypothetical experiments. What if I took this action? And that is what we do with the do operator. And like I said, just doing that is not enough. We also need to be really careful to not be fooled by randomness and quantify the risk of those actions using Bayesian statistics. And I didn't show, but PyMC is a powerful framework that allows you to do that. There's a blog post you can check out on PyMCLabs.io, pymclabs.com. So yeah, that is basically the motivation for Bayesian causal inference. Now, like I promised in the beginning, here's some like super recent stuff that I'm very excited about that I wanted to share. It's a little bit rough. It's very early days. But yeah, I'm very curious to hear whether this makes sense. So we're able to simulate these what if scenarios, right? And make these predictions, right? But they're still only in the realm of like that model, right? They're not real experiments. So obviously, ideally, all right, we can run these real experiments, right? We would go to the marketing department. We say like, okay, for 100 days, do this, and then for 100 days, do this, and just measure. No marketing department ever will do this. They, the CMO, the chief marketing officer, just like has to get the numbers up, right? And he's not interested in knowing the truth. He's interested in like getting the numbers up. So we need to be able to run the next best thing, which is run synthetic experiments, right? And here we can combine tools from generative AI with the Bayesian model and get the best of both worlds. And this is worked together with Dominic Sham of Simulatrix, who has helped on the generative AI side. Motivating in general, what the challenges are facing the industry, especially in marketing, is, well, there's huge demand for this, for experiments and market research, but actually running them is, well, often people don't even want to run experiments. If they do, then it's very difficult. Responses are hard to find. Who really wants to fill out these surveys? Oftentimes they're not very representative either. So it's yeah, expensive, time consuming, and difficult. And yeah, you can't really often find the representative groups that you care about. So there's this thing called synthetic consumers, which promise to help with that. So they're cheaper because, well, LLMs tokens are pretty cheap. They're faster. I just was on a call with a customer where they run studies in minutes that otherwise would take months. They don't sleep. They don't get tired. You can run really long surveys, and you can, if you can simulate your groups, well then, like niche groups, then you can also study them. So, and this is something that I want to talk a little bit about. So here's a cool paper from 2023 that I think was one of the early ones that sort of kicked this off, asking some pretty simple economic questions and seeing whether the LLM, in this case it's GPT 3.5, would respond in an economically sensible way. And the very first question is it price sensitive, right? So the way that the experiment works is you ask it to whether it wants to purchase Colgate toothpaste at a certain price. And then here is how often the LLM said, yes, I want to buy at this price. And so basically for $2, yeah, definitely. And this was actually in comparison with another toothpaste. So so you either pick Colgate or you pick something else. And the other toothpaste was priced at $4. So obviously, if you think both are equally good, you more often would want to pick the cheaper option, right? And then once this becomes more expensive, the Colgate, then the LLM stops picking that. So that's pretty validating, right? It's like the very core, I think, that we want to know, we actually have established here. And then there's a whole bunch of other interesting properties that they test, such as the level of income of the LLM, right? I mean, LLMs, I don't know what OpenAI is paying them, but probably not a lot. But you just prompt it, right? So you say like, you are a synthetic consumer that makes 50,000 a year or 120,000 a year. And then you just respond how price sensitive it is. And you see that that is price sensitive. So the 120K basically is much less influenced by different prices, here's a Surface tablet, than the other one. You can also do other things like establish the willingness to pay for fluoride in toothpaste. And what's interesting here, for example, is that it didn't actually tell it that fluoride is valuable, right? It didn't say like, oh yeah, fluoride is amazing. Would you pay more for fluoride-based toothpaste? But because LLMs are trained on like basically everything, they know that like fluoride is something that has health benefits, right? And this is also the idea of why this is kind of interesting, right? Because if you just say like, oh, well, it's just simulated people, then who cares? But yeah, they do represent the collective knowledge of humanity, basically. Now that's the basics. Here's another paper that came out more recently where they had a questionnaire and then they created different personas. So this is now basically focus groups, right? We want to not just know in general what the average of the population does, but individual groups, right? So like some people are more price sensitive than others. Some people really like Colgate toothpaste. Some people, yeah, like whitening toothpaste, whatever. And then you can cluster these and, well, I'm not going to go into detail here, but basically simulate individual groups. The way they did this here was to assess this using questionnaires. So they asked real people these questionnaires and then simulated this and get different target groups essentially, which is cool. But in this experiment, what we wanted to do was to go beyond that, just simple questionnaires, right? Because questionnaires is kind of simplistic. We're statisticians, we know a lot about this. How do we generate better synthetic consumers with the right preferences? So we take what is called a discrete choice model, which takes sales data over different products over time, and then it outputs preferences of customers, right? So if we sell a lot of whitening toothpaste, then probably a lot of people really prefer whitening toothpaste, right? So just from the aggregate sales data, we can infer what our underlying population cares about, right? And this is what that model does. So that model estimates the customer preferences, things like what brands do I like, what sub-brands do I like, how price sensitive am I, right? If people don't buy hardly any really expensive toothpaste, well, then most of them are very price sensitive, right? So there's all these things we can infer. And this is like now only on data, right? The LLM has nothing to do, but we get like this preference matrix with different clusters, people that care about different things. And just to give you an intuition of how that model works is basically what is the data generative process, right? We assume that there's customers that come into a store and each customer has latent preferences. Like I said, I really like whitening toothpaste. And then they see a list of products and they pick one. So that's where the discrete choice comes from. That matches their attributes. And then that leads to the sales data that we observe. And this is how we fit that model. So once we have this model, right, and we have these preferences estimated based on sales data, we can replace this here. So we don't have to run questionnaires, right? We just have to see the purchase behaviors of people. And then we can use sales data, use our discrete choice model to estimate the preferences, and then basically generate the synthetic consumers based on the different patterns we have identified from the sales data. So we like bridge the statistics, the numbers, and the insights from there with language and these questionnaires. So the first experiment is identifying willingness to pay. And again, this is like just a first cut. It's not quantitative yet, but it's kind of interesting to see. So basically, we sample from we take these preferences, we convert them to Likert, and then we ask the LLM. Actually, you'll see it here. So here is an example. So we prompt this was Opus, Claude Opus. Your customer that favors sub-brand zero and has a moderate sensitivity price adjustment, how much would you pay for a product of sub-brand zero? And then this is the reply from the LLM. So based on my persona as a customer who favors sub-brand zero, I would choose to spend $4 per product of sub-brand zero. So likes sub-brand zero and would spend more. And then you can it just like goes on to explain and reason more through this. Here's another example. Now it's we ask it how much would you pay for a product of the sub brand that you do not favor, and then it would spend less, right? So I'll give you like a second to skim this. The underlying point is, well, we see these so yeah, we can generate these different personas. They respond in interesting matching ways, and they reason about their choices. And for marketing research, you can imagine that's quite interesting. We can also now ask it for feedback on new innovations, right? So let's say we want, we think of like bringing out a new mango flavored toothpaste, and then we ask like, would you purchase it for $1? And then if this is like the thing that it wants, and here, what I also think where it becomes really interesting is that now we really get the benefit of the LLM being trained on contemporary data, right? Like maybe I'm already behind the curve, but a couple of years ago, I love mango, and I think a couple of years ago, mango was like a pretty popular flavor. So the LLM would know that, right? That like people on Reddit, they say like, hey, mango is super cool. And like all that data is in there. And then it would like basically say like, oh yeah, this is like really interesting new flavor and I'm interested in this. It matches my purchase behaviors and my preferences. So we actually get this. And you can compare this, for example, with like a potato flavored or something. I would really that's a little bit weird. And you can also just like show it ads, right? So there's very little limit to what you can present the model with to test it. Here's another example where it doesn't like the brand that like brought out the mango flavored toothpaste, and like, no, I like the other one. Mango is not my thing. So it's kind of fascinating, the things that it does. So to wrap up, this second piece was really about combining numbers, which is the domain of statistics, with the domain of language, which is where large language models excel. And the statistics allows us to use Bayesian causal modeling, which introduced in the first half, to infer latent states and traits from quantitative data that we have measured, in this case, about sales data. And then given this model, we can generate new personas and ask what if scenarios, and then test these as if they were real subjects. Because doing it on real ones is costly and error prone. And this way we can just get a lot of data and really close the loop. And then you can imagine, of course, feeding that data back, right? Because what I showed you was qualitative output. What we want to do then is have the LLM also fill out questionnaires, right? And then these questionnaires feed back into the model as well. And you can imagine all kinds of like interesting workflows emerging where also then we feed that back into maybe an LLM that reiterates on the product and the marketing itself, right? So yeah, we can basically create these very interesting self-improving loops. And yeah, I think that's a really interesting future. The proof is still out how well this will work, but I think it has a lot of potential. So with that, thank you so much for your attention. And if there's any questions, happy to go into that.
Thank you, Thomas.